Hi, it's Alan. I'm back and I'm continuing my lecture on chapter 2, and this is lecture number 4. And this is where we left off. An annuity is unlike the first two formulas and the first two tables, which is one amount, one time only, a one-shot deal. An annuity is the same payment over and over and over again, okay? Now, as long as it's always the same amount, I don't care whether you're moving forward on the timeline or backward, you can take a shortcut by using table 3 or 4, okay? Now, I think based on, it was $8,500 that I'm going to invest every single year starting a year from now. Not now, we'll deal with that later. An ordinary annuity says start a year from now, okay? And the interest rate that we used was 7%. Okay, so I'm going to make 5 $8,500 payments. All right, now, as I demonstrated to you, I can invest $8,500 starting a year from now 5 times. So if you do it the hard way, using table 1, because we're moving forward into the future, okay, my first $8,500 payment happens 1 year from now. It will work for me for only 4 years, therefore. I go to table 1 and look up the TVMF. For 4 years, 7%, and that's $11,141. My second payment goes in at the end of 2 years. That's going to therefore work for me for 3 years. My TVMF is 1.2250. You'll find all of those on table 1, table A. Okay, now you can add them all together after you've done all 5 calculations, and you'll get 48,881 roughly. Okay, now that's 5 operations. I would rather do one operation once, okay? Number 1, it's efficient. Number 2, every time you do a calc, there's a chance you can make an error, so I'd rather do something just once. Okay, so since the payment is always the same, $8,500, total invested will be $42,500, I can instead go to the second table, as I did over here. The 7% column for 5 years is going to give you 5.7507. I multiplied that by one payment, just one payment, and I get my 48,881. So what I'd like to start by doing, as we did the other day, is do a proof. Now I give you that proof in the slides, but I'm going to repeat it here to explain it, okay? Now this proof is going to need one extra column because we are still going to earn interest on whatever we put into this fund, both compounded interest and a series of payments. So I'm going to put my payments out here, payments, and I'm going to keep my running balance going as well. Okay, so now in year 1, 2, 3, 4, 5. All right, what do I have to start with? I make absolutely no interest in the first year. Why? Because I've wasted it, okay? In the first year, I didn't put any money in until the end of the year. So at the end of the year, I put in $8,500. That's how much I have, 0 interest plus $8,500, okay? So at the end of the first year, that's all I have. But now that money is going to work for me in year 2. At how much? At 7%. So I'm going to take that ending balance, friends, I'm going to multiply it by 0.07. So in year 2, my first payment makes me $595, okay? I am then at the end of the end of year 2, going to put in another $8,500. What do I now have? I have the amount of money I put in at the end of year 1. I have how much interest that money made me during year 2. And then on the last day of the year, I put in $8,500 more. And now I have $17,595. Okay? I'm going to replicate is the proper word, all my payments, and on my running balance, all of my interest. I remind you that I'm running an Excel course online that is free of charge. If you'd like to take that course when we're finished with this one, I would be delighted to have you there. Okay? It's like this. It's going to be a series of lectures that I pre-record followed by quizzes. More on that another time. Okay. So, have I given you a proof? Yeah, I think I have. There's my 48,881. Okay? I also show it here in the slides. There is a rounding difference. We're not going to worry about that. Okay? And finally, the last topic I want to cover with you in this module is going to be the present value of an annuity, and this is an important one. This is almost a little more common. How much do I have to invest today to throw off a stream of payments in the future? This is a very popular investment vehicle with seniors. Seniors like to have a certain amount of money invested that will then allow them to withdraw a certain amount in the future as they go to complement their Social Security. I put one of these together for my mother-in-law. You call up an insurance company and say, what do I need to invest today? And then they will throw off payments for you in the future. Okay, so let's say, how much must I invest today? And this is on page 29 to throw me 4 payments of $50,000 each if I earn, and what did I use in the book? I used 4%. Whatever is in this fund will earn me 4%, okay? Now here's what's going to happen. Same thing as before, it's an annuity. But now I'm concerned with how it will throw off payments for me based on what I put in and how much what I put in earns interest. Moving from your left to your right. I put in an amount today, it earns interest. End of year 1. Starting 1 year from now, I pull out a big amount of money. Then it goes up again, what's left. It's not as much, it won't earn as much, but it does go up. Then down again. Up, down, like a set of stairs, okay? And I'll demonstrate that for you momentarily. So you want to answer that question, how much must I invest today? That's present value, backwards on the timeline, okay? So 4 years, 4%, each payment will be $50,000, okay? And if you do it right, when you've invested the right amount of money today, once the very last $50,000 payment is withdrawn at the end of year 4, 4 years from now, the fund is going to be used up. It'll be equal to 0. You want to know to the dollar how much you must invest today. Again, like before, you can do 4 separate calcs, present value, the second table, and add them together, okay? Or you can do it once if the payment is always the same as it is here, and that will be a nice shortcut for you. So what you do is you run over to table D, okay, and we're going to take one $50,000 payment, just one payment, not all 4 of them, just one of them. And if you look up table D, table 4, if you will, the 4% column, 4 years, you're going to find that the PVIFA, as we call it, is 3.6299. So let's math that out and see what we get. $50,000 times 3.6299. It looks like we have to invest $181,495 today. Okay? So we make that investment. That's the amount of money that will fund 4 $50,000 payments, $200,000. Where does the other $19,000 come from? It's going to come from the earning of interest during that same 4-year period. So let's do a proof. I remind you, I will not require you to do a proof, but I encourage you to try them. Okay, I'll list the year first, then I'll list the amount of the interest in the next column because our money will always be working for us. Then I'll list the payments, the withdrawals that we will make, and finally I'll show you how our balance is running down. Okay, now we're going to start with $181,495. Okay, all right. This is going to operate for 4 years, 1, 2, 3, 4, just like that. And once again, I'm going to put pennies on this thing. I don't like using pennies, but sometimes it helps you understand the rounding differences and the degree of accuracy. Okay, very good. So the amount of interest involved in the first year, okay? Now we're not taking any money out until the end of the first year, so that whole $181,495 will be there working for us. We're going to change that up in another assumption later. Let's worry about that in Module 2, Week 2. We're wrapping up Week 1 right now. Okay, that $181,495 goes to work for us immediately, earning us 4%. So I'm going to take that $181,495 and multiply it by 0.04. So in year 1, we are going to make $7,259. Okay? On the last day of the first year, we then take out 50 grand. Okay, so now watch the math here, guys. I'm going to take my starting balance of $181,495, I'm going to add the amount of interest that I gained during the year by that money working for me. And then on the last day of the year, I minus that $50,000 payment. So what do I have after I do that on the very last day of the year? I've got remaining working for me, $138,754. That money will work for me in the second year. So any interest I earn in year 2 will now be based on that number. It's going to be less, of course. Okay? So I'm going to take that same number of payments and replicate that down. 4 payments of $50,000. Whatever is working for me will earn interest and it will be declining. And of course, I take my balance down and look at that. It works. Okay? There's my $181,495. It grew by $7,000 to about $189,000 in the first year, and then I took out $50,000, leaving me only $138,000. That number earned me less, but still earned me something. I take out my second amount. Okay, year 3, same thing. Now at the end of year 3, I only have a balance of $48,077. What happens then? Okay, well that $48,077 is going to grow by 4%. It's going to earn me another $1,900, and that is just enough on the very last day of the year so that I can pull out my last $50,000. Forget the 28 cents. That is, of course, because of rounding, as always. Okay? And once again, I do have a couple of format problems that happen every so often with this Excel system. I apologize for that. There we are. Okay, just to make that consistent with everything else that we did. Okay, so we have seen a proof of the fact that in order to get 4 $50,000 payments, you need $181,495 today. Okay? Please remember, when you're doing a present value, it means you must always have less. Okay? Now, let me end this lecture with one very simple illustration. Okay? This is a very popular application of present value, and I think I'm going to have to demonstrate this in another lecture. But when you win a big money lottery, I don't mean like a $10 scratch ticket, I'm talking like $1 million lottery. Once you put the champagne away and take a Valium, upon winning $1 million, the lottery commission is going to say what to you? Okay, they're going to say, well, we'll give you 10 payments of $100,000 each for the next 10 years, or, starting a year from now, or we'll give you a cash amount. Okay, where did they come up with that cash amount? Which one are you going to take? That's the question. Which one will you take? Based purely on the numbers. You might say, well, I want the money now. Or I question the ability of the state to give me all those amounts in the future. Whatever your reasoning is, and by the way, we're going to completely ignore taxes. Forget about taxes for the moment. Okay? The thing is, you can't answer that question based on mathematics without knowing how to use Table 4, Table D. Okay? The state knows how to use it. The Lottery Commission, they're experts at doing that. So they have to come up with a cash equivalent today that equates to 10 payments of $100,000 in the future. What's it worth today? Can you compare money today to money in the future? No, you can't. They are unlike variables. So to make a valid decision about the lottery, you've got to be able to take all those future payments, discount them to today, and then say how much does that compare to versus the cash amount that they're trying to make me take. Okay? So here's my example from the text. Yep, this is from the text. Okay. You win 20 $70,000 payments. Okay, what is that? That is $1.4 million. Okay, or will you take $750,000 today in cash, again ignoring taxes? All right, how do you solve that? Guys, you can't solve it without an interest rate. So you're going to choose an interest rate. And how you choose that rate, I'll describe later in my next lecture, okay? But you're going to say, basically, by some interest rate, if I discount all those future payments to today, Now I can compare that to the cash amount, the lump sum that the Lottery Commission is offering me, and pick the higher of the two numbers. All right, again, ignore any extraneous factors, please. All right, so I'm going to go to my present value tables for an annuity because the 70 grand they're offering me is an annuity. It's the same amount every year for 20 years. So if you take $70,000 and you go to the 7% column for 20 years on the fourth table, you get 10.5940. That equals 741,580. Okay, so if you discount that 1.4 million stream of payments, it's only worth 741,580 today. Therefore, now that you can compare the two of them, they're on the same playing field, you'd say, I'm going to pick the higher of the two numbers. That's $750,000 in cash. You would take the cash. Okay? Remember, friends, see it on the slide here. You can't compare money in the future to money today unless you factor in the time value of money. Okay? All right. And the interest rate to use, I'm going to wait on that topic. So the very last slide that I want you to be concerned with is going to be slide 31. I'm going to say end module 1 at slide 31. Okay? That's all we have to do. Now, I have a few minutes left, so what I'm going to do is I'm going to show you very quickly if these amounts equate. What are your choices? You're going to take 20 payments of $70,000 starting 1 year from now, okay? Or you're going to take $750 in cash today. That means you want to take the bigger of those two numbers. You cannot compare the 1.4 million in the future to 750 today. So what you do, very simply, is you do like we've been doing, okay? We think we've got the right amount here. Payment, okay. I'm going to put the payment here, and I'm going to put the balance here. Okay. So what I will do is say, in module 1 at slide 1, that's right. So $741,000, let's do a proof. 741,580. Okay. Then I'm going to take these numbers. And I'm going to multiply this out by 18 more periods. Watch how I do this. Okay, 16, I've got to go 4 more years. 1, 2, 3, 4. There are 20 years. I'm going to prove that that 741,480 is going to grow. Okay? I'm using 7%, I think was the number I said. Yes, 7%. So I'm going to take, I like the number 7. What can I say? That number, 741,580, is going to earn me 7%. Okay? I'm going to take a payment of $70,000. Okay? The 741,580, if I had it in cash right now, would be at the end of the first year with $51,000 more, and then I take a $70,000 payment. Okay. Just like I did in the last example, ladies and gentlemen, I replicate my $70,000. If these numbers don't work, I will check them and repost for you because I sometimes make an error on the fly here. And this number should have exhausted itself, and it does. There it is. The annuity will have used itself up. I have just proven to you that $741,580 is what that stream of 20 payments of $70,000 is worth to you today. Okay? So, again, if the Lottery Commission is saying we'll give you those payments for 20 years at $70,000 each, or we will give you $750,000 today in cash, obviously you're going to say, I'll take the $750 because it's worth more than the present value of the future payments. I'm going to leave you with a final rule that we all use. okay, and this is going to come up all throughout the course, ladies and gentlemen, is that in general, okay, the value of any investment, okay, today is worth the present value of all expected future cash inflows. That's a key rule, ladies and gentlemen, okay? And one of the reasons that I put Chapter 2 so early in our studies, or I put the contents of Chapter 2 so early in our studies, okay? When you're trying to determine the value of stock, of bonds, of any financial instrument in the future, you say to yourself, what do I expect to make in the future? Then you say, if I take those future values and discount them, Table 2 or Table 4, to today, all right, what is it worth? How much should I pay for it? There's your answer. Okay? That is all for today. We have now concluded the lectures for right on time. You heard my timer. We've now concluded our lectures for Module 1. This is the fourth of our lectures on Chapter 2. And you should have everything you need. And I'm going to give you a homework assignment very shortly in the module. And then I'll decide whether I want to do it with you by video or not. Okay, so we'll deal with that. Thank you very much for your kind attention. And get in touch with me with any questions at all. And please have yourselves a good rest of the weekend. Bye-bye.